Hello everybody and welcome to video 2 for Cumulative Review Packet number 13. We left off here on number 5, plugging in the values -1, -2, -3, and -4 into the function 2x plus 3. So if I continue to do that, if I multiplied this, I'd get -2 plus 3, so I'd get 1 as my output. -4 plus 3 is -1. -6 plus 3 is -3. And then -8 plus 3 is -5. So if I plotted the points -1, 1, this time, because x does not exist at -1, I would have an open dot at this point, or a hole. I then will plot the rest of my points, -2, -1, -3, -3, and then -4, -5. And because the graph only exists less than -1, I would start at -1, go toward the left, towards -infinity, and so I'd have a line, and let me redo that to make sure it's a little bit nicer here, but I'd have a line, starts at the hole, -4, -5, and goes down this direction, with an arrow, because it goes all the way down to -infinity. And so this would be my piecewise graph. Now that I have my piecewise graph, I can answer some of the following questions. If I'd like to find f of 0, that means that I'm plugging in x equals 0 and looking for the y value out. So if I look at 0 and go down to the graph, the y value is -4. If I look at f of -2, that means I'm plugging x equals -2 into this function. So if I look at the x value of -2, the y value that goes with it is -1. f of 4, I go over to x equals 4, and it looks like it's somewhere around here, but I'm not exactly sure because we didn't use it in our table. So what you would do in this circumstance is look at x equals 4 and ask yourself which interval would it make more sense for 4 to be in, greater than or equal to -1 or less than -1. I would say it makes more sense in this interval, which means I'm going to plug -4 into the function x squared minus 4. So if I did 4 squared minus 4, I would get 16 minus 4, or 12. Last but not least, if I want to find f of -3 plus f of 1, again, this is really a y value plus a y value. If I look at x equals -3, the y value that goes with -3 is -3. So you'd have -3 plus f of 1. If I go over to 1, the y value that goes with it is also -3. So my answer would be -3 plus -3, or -6. Moving on to number 6, which is another piecewise function, you again want to use tables to help and answer the questions once it's graphed. This one has 3 pieces. If I look at piece number 1, which is a line, x plus 1, it only exists when I am less than or equal to -3. So I start my table at -3, and some values below this would be -4, -5, and -6 to start. If I take all of those numbers and plug that into x plus 1, that would be -3 plus 1, or -2, -4 plus 1, -3, -5 plus 1, -4, and -6 plus 1, -5. So if I plot these points, -3, -2, I notice again that it's less than or equal to, so -3, -2 will be a closed dot. -4, -3 would be here. -5, -4 here. And -6, -5. So this one is from -3 all the way to -infinity, so I'd have an arrow like the last example going down forever. So that's piece 1. Piece 2 is just the equation y equals 4, because f of x is really y. Y equals 4 is a horizontal line, and so if I think about the big picture, I'm going to have a horizontal line here at y equals 4, because it's going through the y-axis at 4. However, this horizontal line only exists between -3 and 0. So if I go over to -3 and up to 4, this would have an open dot, or a hole, because there's no equal to, and this also would be an open dot, because there's no equal to. So my line would look something like this. -3 up 4, open dot, 0 up 4, open dot, and I have a horizontal line between those 2 points. Last but not least, if I have this blue graph, x squared, it exists when x is greater than or equal to 0. So I would start at 0. Greater than 0 is 0, 1, 2, 3, at least to start. I plug those all into x squared. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. So if I graph all these points, 0, 0 is here. It's greater than or equal to, so it is a filled in dot. 1, 1, 2, 4, and 3, 9. Make it look like a parabola, because something squared is always a parabola. So it looks like about half of a parabola to me. And so that would be the graph of my piecewise function. And I want you to notice that wherever there is a hole, there is a value that actually exists. And there's a hole, there's a value that actually exists. With that logic, let's look at f of negative 3. If I go over to x equals negative 3, the y value that is actually there is here at negative 2. So my answer is negative 2. If I look at f of 0, I look at x equals 0, and I notice that there is a closed dot at 0 and an open dot at 4. So at 0 is where the point actually exists. That's the y value. F of negative 6, if I go over to negative 6 and down to my graph, the y value is negative 5. And last but not least, f of negative 10 is not necessarily something I graphed. I could guess, but if I'd like to make sure about that, negative 10 is in the green interval. It's less than or equal to negative 3. So I would plug negative 10 into the function x plus 1. So I get negative 10 plus 1, or negative 9 is the y value. Minus f of 2 would be over to 2. Looks like the y value is 4. So my answer would be negative 9 minus 4, or negative 13. Now I know this was not on your packet, but just for a little extra practice, what if I asked you to find f of negative 2, for instance? And the reason I want to point this out is if you go over to negative 2, notice that any value between negative 3 and negative 1 is going to be the y value of 4. So because negative 2 is between these two dots, the y value would be negative 4. Same thing if I asked you for f of negative 1, the y value would be 4 also. Just thought I'd point that out in the video. So changing gears from graphing is what we've been doing recently, multiplying radicals. So I'm going to go example by example, and we would like to try to find perfect squares if possible. So if I look at number 7, 16 is a perfect square, and x to the 6th is a perfect square because the exponent is even. So if I'd like to take the square root of 16 is just 4, and the square root of x to the 6th is really x to the 6th to the 1/2 power, or divided by 2, so it would be x to the 3rd. Number 8, however, does not have all perfect squares like number 7. 28 is not a perfect square, a to the 5th is not a perfect square, but b to the 4th is. So this is when we split into the perfect and non-perfect pile. You would look at 28, and you would think about all the number pairs that multiply to be 28, but really only think about perfect squares, 1, 4, 9, 16, 25, 36, and so on. I know that 4 times 7 is 28, and so if I put 4 in the perfect squares and 7 in the non-perfect squares, that can get me started. A to the 5th is not perfect because this exponent's odd, but we put the closest even number to 5. So if we split a to the 5th to be a to the 4th times a over here, we would have perfect and non-perfect. B to the 4th is entirely perfect because of its even exponent. So my final answer would be square root of 4, 2, a to the 2nd, b to the 2nd, root 7a. Number 9 has the same logic as number 8, but just has a little bit bigger numbers and more non-perfect squares. If I look at 72, again, the most popular pair is 9 times 8 to think about. However, if I write 9 times 8 as an option, 9 is a perfect square that goes in, but 8 could keep splitting. So I would say a better pair is 36 times 2. So I put 36 in the perfect pile, 2 in the not perfect pile. x to the third, we need to split x squared times x. Y to the seventh, we need to split as y to the sixth times y. And then z is just not perfect because it's z to the first, so it would go in the non-perfect pile. So my final answer would be square root of 36, 6. Square root of x squared is 2 divided by 1, x or x to the first, y to the third, root 2x, yz. We don't take the radical off the second piece because none of those are perfect. Number 10. The reason this example is on here is because I like the 5 in front to remind you that that means you're multiplying. So if I look at just the radical first, I look to see if everything's perfect squares. The 36 is, the x squared is, but the y cubed is not. So let's leave the 5 out front and leave as a multiplication symbol. And let's split this into perfects and not like the previous two. 36 is entirely perfect, x squared is perfect, but y to the third we could split into y squared times y. So I'd have 5 times, if I simplify this piece, that is 6xy root y. The 5 and 6 can then multiply, so my final answer will be 30xy root y. Number 11. This is a good problem because it reminds you about what you can and cannot multiply or change with radicals. Whenever you see two regular numbers, you're more than happy to multiply those. So 4 times 2 would get me 8. If you see two numbers underneath a radical, you'll learn eventually that you cannot add them, but we can multiply them. So if I have root 12 times root 3, that would really be root 36. Now, unintentionally, I have a theme here of a lot of root 36s. I wouldn't expect that necessarily on your test. I just like these problems as a whole. Now, 11, you wouldn't leave your answer as 8 root 36 because you could reduce root 36 to just be 6. But then just like number 10, the 8 is multiplying, so my final answer would be 48. Last but not least, in the multiplication category, we have an example that we look at both pieces and both 6 and 3 are not perfect squares, but if we combine them together, maybe it can help us in the long run. So if I go from 2 radicals to 1, I would get 18 x to the, well, there's 2 x's and then 7, so it'd be x to the 9th, y to the 14th power. I then would need to resplit this into the 2 piles and find a multiplication fact that can help us get perfect square and not. So to get 18 originally, we had 6 and 3, but if I took 18 and resplit it, I'm thinking 9 times 2, because 9 is a perfect square. X to the 9th, we'd put 8 of the x's here, 1 of them here, and y to the 14th is entirely perfect. So my final answer for 12 would be square root of 9, 3, x to the 4th, y to the 7th, you divide the exponents by 2, root 2x. All right, moving on to number 13, we are asked to divide the radicals this time. Good news about 13 is that 50 and 2 separately are not a perfect square, but if you recall in class that I talked about that you can go from 2 radicals to 1, this is really the same as the square root of 50 over 2 inside a single radical, which is really the square root of 50 divided by 2, or 25. So this answer really just ends up being 5. Number 14, however, I don't have a perfect square on top and bottom, and unfortunately I do have a radical in the denominator. So what we'd have to do is rationalize. We would need to multiply top and bottom by the square root of 6, and if I do so and multiply straight across, I would get 2 root 6 on the top because these are not like terms, but in the denominator I would get root 6 times root 6, which would be root 36, which is really just 6. So I have 2 root 6 over 6. And then like the quadratic formula, I notice I can reduce the 2 and the 6 to be 1/3. So my final answer would be root 6 over 3. We're going to continue with number 15 on video number 3. Thank you.